We all kind of think we know what light is, right? It's that stuff that travels in a straight line, like a laser beam. Well, it turns out that's really only half the story. Today, we're going to dive into the secret life of light to uncover its true, wavy nature. Let's get into it. I mean, for centuries, this was the leading theory. You had brilliant minds like Descartes pushing this idea. And it kind of makes sense, doesn't it? A beam of light is just a bunch of tiny little particles, corpuscles, they called them, just zipping through space. But, if that's all there is to it, well, that creates a huge problem. A huge problem with things like this. What is going on here? You don't see a prism anywhere, there's no rainbow in the sky. So where did these beautiful shimmering colors come from? They just seem to appear out of thin air. And yeah, that simple particle model, it's got no answer for this. To crack this mystery, we have to start thinking about light in a totally new way. And that new way, well, it's to stop thinking of light as a particle and start thinking of it as a wave. Seriously, this one little shift in perspective, it unlocks everything. And it all starts with an idea that's as simple as ripples in a pond. Okay, so the big idea we need to get our heads around is something called a wavefront. It sounds technical, but it's not. Just picture dropping a stone in a lake. You see those ripples spreading out? The wavefront is just that outer circle connecting the very top, the crest, of all those ripples. That's it. It's just the leading edge of the wave. All right, this might look a little complicated at first, but don't worry. The key thing to notice is the difference between a point source and a plane source. See how a source that's close by, like a light bulb in a room, creates these expanding spherical waves. But what about a source that's super, super far away, like the sun? By the time those waves get all the way to us, they're so big they basically look like flat periel sheets. And we call those plane wave fronts. Simple as that. So way back in the 17th century, this Dutch physicist, Christian Huygens, he had this absolutely brilliant aha moment. He realized you could figure out how any wave moves forward using just one simple but incredibly powerful idea. And here it is. This is his principle in a nutshell. First, you just imagine that every single point along a wavefront is like its own tiny little pebble dropped in the water, sending out a brand new mini wave. They call them wavelets. Kinda cute, right? Then, step 2, the next wavefront, just a split second later, is just the line you get by connecting the outer edges of all those new little wavelets. It's like a chain reaction, ripples making new ripples that make the next big ripple. Okay, so why are we getting so into this? Why does this matter? Well, because with this one simple rule, all of a sudden we can explain a ton of stuff about light that just didn't make any sense before. Let's take refraction, for example, the way light bends. When a light wave hits something like water, one edge of the wave enters the water first, right? And light travels slower in water, so that part of the wave slows down. According to Huygens' principle, its little wavelets don't travel as far as the ones that are still zipping along in the air. And what does that do? It causes the whole wavefront to pivot, to bend. It changes direction. And here's the really cool part, the magic of it. This isn't just some vague, hand-wavy idea. Huygens' principle lets us calculate the exact angle of that bend. I mean, perfectly. The wave theory doesn't just say, oh, it bends. It predicts exactly how much. This thing has real predictive power. All right, so we've established it. Light is a wave. Cool. But that opens up a whole new can of worms. Like, what happens when two light waves run into each other in the exact same spot at the exact same time? Do they just, bounce off each other? Nope. The answer is way, way weirder. So there's a rule for this, and it's called the principle of superposition. Sounds fancy, but honestly, it's just basic wave math. You just add the waves together. That's it. If the top of one wave, a crest, meets the crest of another, they add up and get bigger. If a crest meets the bottom of another wave, a trough, they subtract. And this simple math leads to two totally wild outcomes. First, you have what's called constructive interference. That's when two wave crests line up perfectly. They combine and you get a bigger, brighter wave. But then there's destructive interference. This is where a crest meets a trough, and they completely cancel each other out. Let that sink in. You can add light to light and get total darkness. How is that even possible? Yeah, that idea was so bizarre, so out there, that it absolutely needed some hard proof. So In 1801, a scientist named Thomas Young came up with what might be one of the most famous experiments in all of physics. It's called the double slit experiment. He took a single light source and he shone it at a wall that had two tiny, tiny little slits in it, super close together.
Okay, now stop and think about this for a sec. If light was just a stream of little particles, like firing tiny paintballs through those slits, what would you expect to see on the screen behind them? You'd see two bright lines, right? One for each slit. Makes perfect sense. Except that is not what he saw. Not even close. Instead, he got this incredible pattern, a whole series of alternating bright and dark bands. Those bright bands? That's where the light waves from the two slits were interfering constructively. And the dark bands? That's where they interfered destructively. That's where light plus light was making darkness.
There was just no other way to explain it. The particle model, it was dead. Finished. The double slit experiment proved it, beyond a shadow of a doubt. Light behaves like a wave. And that was a monumental shift in how we understand reality itself. But wait, the story isn't over yet. Okay, so light's a wave, we've got that. But what kind of wave is it? I mean, is it like a sound wave, which kind of pushes and pulls the air? Or is it something different? Well, it turns out there's one final secret property of light that gives us the answer. And that property is called polarization. So the easiest way to think about this is to imagine a wave on a rope. You can shake that rope up and down, or you can shake it side to side. That's a transverse wave, because the shaking part is perpendicular to the direction the wave is moving. A sound wave isn't like that. It's longitudinal. It just pushes and pulls in the same direction it's going. And here is the absolute key. Only transverse waves, the rope-like ones, can be polarized. So let's see how this works. Step 1. Normal, everyday light is what we call unpolarized. That just means its waves are vibrating in every single direction at once. It's a total chaotic jumble of up and down waves, side to side waves, and everything in between. And this is the light that's about to hit our first filter. Okay, step 2. We take that messy, unpolarized light and we pass it through a filter that's kind of like a picket fence. It's got vertical slots. What happens? Well, that filter blocks all the side-to-side vibrations. It only lets the up and down vibrations sneak through. And just like that, the light that comes out the other side is nice and neat. It's polarized. And now for the grand finale, the last step. This is where it gets really mind-bending. We take a second filter, another picket fence, but this time we turn it sideways, so its slots are horizontal, and we put it in the path of our neatly polarized light. What happens? That first filter let the vertical waves through, but this second filter blocks them completely. And the result? No light gets through. Darkness. And this simple, brilliant experiment proves that light has to be a transverse wave. And believe me, this is not just some weird physics experiment. This is the tech working inside your polarized sunglasses right now. That annoying glare bouncing off the road or the water, that's horizontally polarized light. Your sunglasses block it. It's also the secret behind how 3D movies work. They send a differently polarized image to each of your eyes. But even more important, this whole idea confirmed that light is a transverse electromagnetic wave, which is like one of the absolute cornerstones of modern physics. So, let's just recap. We started with light as a simple little particle, and now we know it's a complex wave that can literally cancel itself out to create darkness, and it has a secret hidden direction. It just makes you wonder, right? If light can be this strange, this counterintuitive, what other incredible secrets is the universe hiding right in front of our eyes?